Okay, our next speaker is William Booth. Will has worked at CERN since 2011, initially on simulation of cryogenics, followed by joining the team of PLC developers working on cooling and ventilation applications. Lately, Will has led the CV PLC development team, and a large task is currently being prepared for the upgrades for the LHC in the long shutdown in 2019. Thanks, Will.
Today I'd like to present the work we've done towards the virtual control commissioning of the ventilation control system for the CMS experimental Cavern. This work was done by Samuel Soriceau, Benjamin Bradu, Enrique Blanco, and myself. The LHC has been in operations, as you know, since 2008, and there's been no major improvement on the control system of the ventilation of the Atlas and CMS caverns since that time. The decision was made to upgrade both the Atlas and CMS ventilation control systems during the LHC long shutdown 2 in 2019 in order to solve the obsolescence problem we have with the current SCADA system, WISCON, which is not supported anymore, and to address the fact that the PLCs are nearing their end of life. We also would like to migrate the control system to the CERN Unicos framework, as used by other control systems at CERN, cryogenics, and all the new cooling and ventilation systems. And we need to take into account operational experience gained during the last 10 years of operation to avoid any unnecessary manual operations during startup and switchover, for example. The constraints, as Eric said, the CMS ventilation plant is running 24 hours a day, 7 days a week. It's critical during the LHC run to maintain a stable under pressure for safe operation. Immediately after the run, we need to purge. During the technical stops, when people are in the cavern, we need to maintain airflow, and we will only have a limited intervention time. So how best do we ensure a smooth upgrade? As Eric said, recommendation 1, prepare everything beforehand. We call that virtual commissioning. Virtual commissioning is entirely offline, has no impact on the installation. We use a dynamic simulation model to validate new control strategies and operational strategies, and we also use this for operator training. This is a slide to outline the approach. First of all, we have the process and experimental analysis. Sorry, the font is not very readable. We developed the physical model, initially working on an HVAC library, validating the library, building small, simpler ventilation models to validate that we can use the ventilation library, component library we've developed. Then we built the CMS experimental cavern ventilation model. Then we embed in that model a simple control system and write preliminary specifications, what we call a functional analysis, AF. Then we use that model for simulations to evaluate possible improvements, upgrades with feedback with the customer. Finally, we implement that in the PLC and can perform virtual commissioning in the lab with the dynamic simulation and the PLCs connected. This is an overview of the CMS buildings, both on the surface and underground. You can see it's a very large installation. There are 11 PLCs controlling the ventilation systems in all these buildings. We decided for critical reasons to focus on the experimental cavern of CMS shown here. The ventilation units are actually installed on the surface, and there's a shaft connecting the two. We started by performing a detailed analysis of all the available documentation in process and instrumentation diagrams, general assembly drawings, HVAC maintenance reports. Combine that with as-built subcontractor documentation available from when the system was installed in 2000 to 2005 to generate reliable input data for the model that we will ultimately build. Then we started building an HVAC library. We used the tool EcoSim Pro that's been used at CERN for a number of years to develop cryogenics and cooling simulations. In 2014, an initial version of the HVAC component library was built. We improved the library. Each of these component elements, which include fans, heaters, cooling coils, dampers, is essentially a model, a physical model of differential equations governing the behavior of the component. So zooming in on one, this is a fan. To give you an example of the detail, we look at the corresponding fan curve that can be entered. So you take it from the supplier data sheet showing the correlation between pressure drop and airflow. You also have the data related to rotation, fan speed, and fan efficiency. Then we embed a model of an ideal heater, which allows us to model losses in the fan, in the transmission, and in the motor itself. And we can also make additional calculations like motor energy consumption. Once we've built the library of components, we needed to validate both standalone tests on the components themselves to ensure that they matched data in the thermodynamic tables, as well as blind tests where we assumed that we didn't know the internal equations, and we checked that the basic thermodynamic evolution matches what we would expect. So for example, a heater, you would expect the dry temperature and specific enthalpy to increase, the relative humidity to decrease, and the absolute humidity to stay the same. And we check those against the psychrometric diagram. Next, in order to validate the library that we have validated the individual components, we took a number of installations, simpler installations at CERN that we had available data. For example, we took a room in the CERN Computing Center and built a small ventilation model using the library that we developed. We pick a simple ventilation system which has similar components to the ultimate installation, the ventilation of CMS, and we use the available data to validate the model. And we're also able to use this model for simple control studies to optimize control algorithms. To give you a few more details on this particular example, here's an overview of the supervision of the 513 room, where you can see that the room being ventilated at the bottom right, the air handling unit at the top left, and a fresh air damper and a recycling air damper and a couple of sensors. Zooming in on the air handling unit, you see that we have shutoff dampers, we have a cooling coil and a fan, a centrifugal fan. That model shown in EcoSim Pro, the simulation tool that we use, you can see that there's a correspondence between the elements. Here we're not depicting control elements. You can see the air handling unit and the room itself. Zooming in on the air handling unit, you see all the physical components represented, and then we perform simulation results. To tune the model, we need to plot basic parameters such as airflow, combining the fresh air and the recycled air to allow us to tweak the damper coefficients. And we then can correlate that against available measured data. So here's a 5-day simulation. We see there are slight discrepancies, and this is not necessarily due to a bad model tuning. It could be due to the heat load, which we had to estimate. We also look at more than just one parameter. We compare whatever parameters are available. Relative humidity is shown here compared against real data, and the cooling coil position. So once we performed this, we could then go into or develop the model of the CMS ventilation cavern itself. Just to give you an overview of the system, this is the process and instrumentation diagram with the cavern shown at the bottom, the two large supply air handling units at the top left, the main extraction air handling units in the center, and the gas extraction smaller units just to maintain the under pressure on the top right. So you can see the analogy again between this process and instrumentation diagram, which is the real equipment installed on site, and the EcoSim Pro model shown here. We have the cavern, some leakage to the surroundings, the supply air handling units, the extraction air handling units, and the gas extraction under pressure units. Zooming in on the air handling units themselves, you can see that two air handling units are individually modeled on the left, and we have an equivalent model of the damper models, which we had to modify slightly to deal with issues of backflow. And in detail on the air handling supply unit itself, we see the 2 air streams, the damper models, the filters, the pre-cooling, cooling, post-heating, and the centrifugal fan. So now we've built the full model. We need to embed a control. In order to do that, we had to write a preliminary version of the functional analysis because it wasn't yet available from the customer. We did that following the Unicos, which is the control standard we intend to adopt, and embedding some improvements that we learned from the operator community. Then we used that model with the embedded control to run various simulations of different operating scenarios, and using that, we iterated it with the functional specification. Ultimately, once we get the final specification from the supplier, we'll be able to implement that, as I said at the beginning, in the PLC, and then run a virtual commissioning. Here I have a couple slides showing one example of startup gas detection in the experiment, in the Cavern itself, with the cap open. In this case, both air handling units start to run after a certain amount of time while the dampers are opening. We see that both air handling units start blowing at 45,000 cubic meters per hour, and all the exhaust goes through the cap. So you can see that the model makes physical sense. We also see the initial outdoor air temperature rises slightly as soon as the air handling units start due to the heat due to the motor load. And we see a slight increase in temperature on the wall in the Cavern. And we also, since we're interested in maintaining an under pressure in the Cavern, we plot Cavern increase in pressure. Again, we would need additional data to validate the absolute amplitude, and we can plot modulating damper positions over the transient. Finally, we were able to set up a dynamic simulation with PLCs in the loop. This is the precursor. Once we have the final software, for now the PLCs have what we call a version 0, which is just the inputs-outputs, so it allows us to manually manipulate the model from the supervision. Following the schematic on the left, we have the EcoSim Pro model dynamic simulation running as a standalone executable, interfacing with OPC with the PLC, Schneider PLCs in the lab. There are 3 in this case. That PLCs are connected as we normally have in the control room to the supervision system, which is then available in the lab for users to. The idea would be we could give this to the CV community, and they could run various operating scenarios while they're writing their requirements. And we'll be able to come back and use this setup once we have the full control system implemented. So in conclusion, we were able to improve and validate the HVAC component library that was developed for EcoSim Pro. We have modeled various small HVAC plants around CERN, and we obtained good comparison with data. We built a full model of the experimental Cavern of CMS ventilation system with all the technical inputs now known or estimated, and resolved the simulation issues of convergence and simulation time. We ran a number of simulations with simple model control covering various operating scenarios, hooked up 3 PLCs in the lab for manual simulations. Currently, the development of the control system is ongoing, as I said, with the cooling and ventilation team at CERN, and as soon as we have the complete system, which we're hoping to by the end of the year, we'll be able to perform the virtual commissioning. Thank you very much.
Yeah, I was curious, do you have any way of modeling the airflows within the chamber, or do you need to do that?
We don't take into account the airflows in the chamber. For now, it's a 0D model. They have more complicated finite element models in the cooling and ventilation group, but since the goal of the model is to be able to hook up the control, we don't need that kind of detail.